Hey guys, uh, welcome to our first day of graphing. It's going to be at least a couple of these. Um, when I say graphing, I mean graphing quadratic functions, like this is right here. Um, so graphs of quadratic functions they all look similar. There's kind of a U and an upside down U, and the word that we use to describe that is the word parabola. 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 And a parabola looks like a U. And we're going to graph one of them like point by point, and then I'm going to tell you what happens. I'm going to describe some transformations, and then I'm going to talk about vertex form. So basically, like all graphs, like this is x on the horizontal scale, and this is f of x or y on the vertical scale. And we graph, like the way you graph functions is you plug an x into here, and that tells you how far left and right to go, and the answer that comes out tells you how far up and down to go. For example, if I plug a -2 in here for x, -2 squared is +4. So that's a point right here. X is -2, fx is +4. I plug a -1 in, I get +1, 0, then I get 0. 1 and 2 give me +1 and +4 respectively. I can plug in 3 just because I know that 3 squared is 9. I get a shape that looks something like this. So it's kind of like a U. It shouldn't be as pointy at the bottom, but it's a little tough here drawing with this tablet to get it to look right. But that's what a parabola looks like. It looks like a U. It could be upside down. It could be slid left and right. It could be a little wider, a little skinnier. There's a lot of transformations we can do. In the next few slides, I'm just going to show you what those are. And then there's going to be a kind of a summary slide at the end of those, which is going to be one you're going to have to know the answer. You're going to have to know all the information on. So if I transform the x squared, actually, let me go back real quick. Name this. This is y equals x squared, or f of x equals x squared. This is called the parent function, because like all the other functions are like, they're like kind of like children of it. They're like are derived from it. So we start with this one, y equals x squared. And then if you add 2 to a quadratic function like that, it just slides the whole graph up 2 units. So where before we were at 0, 0 to begin, now we're at 0, 2. And every point got moved up 2. There was a point we had before at 1, 1, and now that point is at 1, 3. We got a point at 2, 4, a point at 2, 6, and so on and so forth. So +2 moves it up 2. Maybe not surprisingly, a -3 on the right here will move it down 3. So I would call these vertical translations. That's the word you would use to describe these. Vertical translation up 2, vertical translation down 3. You might guess the next thing we'll discuss is a horizontal translation. Sometimes the word shift is used, like a shift up and down. I tend to say translation, but you can say either one. So if you kind of look maybe carefully at the difference between the vertical shifts or translations, you add 2 like x squared plus 2. But for the horizontal translation, you do you add or subtract on the inside. So you can see here, if you do a minus a number on the inside of the squared thing, it moves it to the right. This is like a translation. These are called horizontal translations. And it's like left and right, and you can see that putting a minus a number inside the x moves it to the right, adding a number inside to the x moves it to the left. Because it used to be at 0, 0, and now it's at 0, +3. Horizontal translations, minus on the inside or plus on the inside. And then upside down flip is if there's a negative on the outside. You can see it used to be the upward U, now it's an upside down U, but you can see all the points are the same. It was 0, 0, and 1, 1, and -1, 1, and now it's like 0, 0, and then 0, you go down 1, and you go down 4, so you're going up 4. I would call this a reflection. maybe even like a vertical reflection because we're flipping it upside down. Then we have these two. So I drew two of these. It's probably a little harder for you guys to tell. You can probably see it in the video. The notes are probably not in color. But the blue graph here, which in this case is the outer one, this is y equals x squared. And this inner one is y equals x squared. So like when you put a number, like a number on the outside here, note that this number is larger than 1. It likes it makes it skinnier. This is called a vertical stretch. Some people call it a horizontal shrink, but I tend to just think about everything in terms of stretches, so I don't have to think about two different words. It's like this. The green one is the green one is the transformed version. 2x squared is on the inside, and x squared is on the outside. So you can see when you put a 2 on the outside, it makes it skinnier, basically. Skinnier. Skinnier is not a math word, but it's a very descriptive word. And here, when we multiply a number on the outside, like it's here was 2x squared, now it's 1/2 x squared. Since this number is less than 1, you can see that the outside one is now, this is y equals 1/2 x squared. And so we've done what I would call a horizontal stretch. And it's like it got wider. So when we multiply numbers on the outside, if the number we multiply is larger than 1, it stretches it vertically. If the number we multiply is less than 1, or a fraction, not less than 1, but like between -1 and 1, then it makes it wider. So skinnier, wider. And now we shall summarize. And then we'll talk about vertex form, and then I'll probably break this video and do some of these practice problems. So plus k on the outside means vertical shift up of k units. Whatever this k number is, you shift that far up. Minus k is a vertical shift down of k units. If the number added or subtracted is on the inside, it's a horizontal shift. Horizontal shift of h units. Shoot, I should have said which direction. Horizontal shift to the right if the number is subtracted. If the number is added, we do a horizontal shift left of h units. We saw a negative on the outside, flips it upside down, so I'll call that a vertical reflection, like over the vertex. It doesn't really matter. The whole thing gets reflected. We're not going to be that detailed today. Okay, these are the horizontal and vertical stretches. That number is a fraction, like less than 1. That's a horizontal stretch. This is a vertical stretch if the number is larger than 1. So there's maybe more than one way to talk about how much it stretches. We'll look at that a little bit, hopefully with some graphing programs in class. But for now, you can just think those are horizontal vertical stretch. We put all this stuff together in what we call the vertex form of a quadratic equation. And that looks like this. Y equals a times x minus h squared plus k. This is called vertex form. The vertex is this point right here, and all these parabolas. All these parabolas, the vertex is that point right at the very bottom, in this case, or the very top, in this case. It's the minimum y value for all these. It happens, it's the maximum when it's upside down. So that's called the vertex. And if a quadratic is in this form, the vertex of that quadratic is h comma k. And you can see there's an h right there and there's the k there. And those kind of come from the shifts. And what the number a does is it affects the vertical or horizontal stretching of it. Like if a is 1, there's no stretch, and if a is 2, it's a vertical stretch, and if a is 1/2, it's a horizontal stretch. And we kind of saw that here. Right, we saw the horizontal vertical stretches, and we saw them here. This is a vertical stretch because it's skinnier. This is a horizontal stretch because it's wider. H is the horizontal translation, which we saw earlier as well. When you add a number to the x on the inside, it moves it left to right. And we saw this, the first translation we looked at. If we add a number on the outside of the x squared, that moves the parabola up and down. So we're basically going to try and do at least 5 points to graph all these things. So the answer to this question, is there a faster way to get the points we need? Yes, I'm going to talk about this in the next video.